Okay, next talk is by Nanako Momiyama. She's from University of Darmstadt. She's doing her master's thesis, and she's giving a talk on FreeBSD Fastpath.
Okay, thank you, Guido, and thank you all for coming the last session. I'm so grateful for coming and for joining this conference. My name is Nanako. Today I'm going to talk about my hacking on FreeBSD to improve IP forwarding performance. Okay. So in this session, I will talk about the software switch routers, which running on top of the general purpose operating system. In this case, the FreeBSD is used as our base operating system. This talk is especially focusing on the idea how to improve the performance of our packet forwarding by using existing kernel network stack. So I'm Nanako, again, and I'm the first-year master's student, majoring in computer science at Technical University of Darmstadt in Germany. I graduated Keio University in Japan, and most of this work has been done as my bachelor thesis when I was in Japan. I'm using FreeBSD and the NetMap framework as my research target, and also as a research platform. So I'd like to start to explain the background and the motivation of this talk. So this picture shows how today's server looks like. There are many VMs or containers on a physical server, and there's multiple NICs. And these virtual machines or containers are usually deployed and managed by our various software tools. And the big difference between the previous non-virtualized server and today's virtualized server is that where the last network hop happens. So in the previous one, the last hop is the hardware switches, which is located outside of the server. But now, in today's case, the last network hop is within the server. So the disk switch where the last network hop happens is called virtual switch or vSwitch in general. And so what the virtual switches do? The virtual switches are implemented as a part of our kernel network stack, such as Linux Bridge, FreeBSD Bridge, and so on. So these are interconnects our VMs or containers and network interface card. And the packets could be forwarded from NIC to NIC, or from NIC to VMs, and also from VM to VM. They can have our L2 routing bridge functions, and also sometimes have L3 IP routing function for managing the VMs in the different subnets, or sometimes have more rich functionality, such as firewalls, for example. So when we assume today's the server architecture, we can find the problems with traditional virtual switches. One of them is that fact that the packet forwarding of these traditional virtual switches is very slow. So there's a situation that the network capacity is increasing to 10 Gbps, 40 Gbps, and they are already very common in the market. With these very high bandwidth network interfaces, it is very difficult to saturate the bandwidth, especially with the short packet. So why there the gap between the increasing network capacity and the actual software packet forwarding performance. Then the one reason is being a part of general purpose network stack comes other overhead. For example, so each single packet is processed by the protocol stack in the kernel. And also, we need to consider the time budget per single packet. So the maximum packet rate on 10 Gbps with shortest packet is 1488 million packets per second. Why we use the million packets per second instead of BPS to describe the performance is that our shorter packet requires higher packet rate to saturate the bandwidth. So to achieve the peak packet rate, per packet time budget is only 67 nanoseconds. So it is very short time, or even in the kernel. So to solve this performance problem, our new approach, which is called user space networking, has become popular. And it exploits our fast packet I/O frameworks such as NetMap or DPDK. And application uses the library provided by these fast packet I/O framework to bypass the kernel network stack, which consumes a lot of time to process the packets. So this approach actually has demonstrated our impressive performance over 10 million packets per second with shortest packets. So it's a very good solution in terms of performance improvement. But here, there's another problem. So there are engineering problems with user space networking. When you deploy this solution to the production system, for instance, these packet I/O frameworks requires existing application to be modified because the API which provided by these frameworks do not any compatibility with existing kernel APIs. So there are also some problems about our scaling of number of VMs and ports, and also it uses some busy pouring, and it becomes the problem to CPU usage, or the software maintenance support could be the problem also. So the approach is in contrast. Addressing these new problems of user space networking, our approach is improving performance of kernel network stack itself. So the advantage of this solution is that we do not need to modify any application. So if you want to use some existing routing daemons, you don't need to modify anything. So you can use our existing kernel routing sockets and then kernel APIs, CLIs. Then, so in order to improve the performance of our kernel network stack, we should raise the performance bottleneck in the kernel. So the default FreeBSD, for example, can forward the packets at the 1.4 million packets per second. So since our 10 Gbps line rate is 1488 million packets per second, so this is just 10% of potential rate. Then, so we started to follow the conventional wisdom, which is the packet I/O and load lookup are slow. In reality, there are a lot of research to address this performance problem of packet I/O and the load lookup algorithms. So the idea is that, so what if we apply these techniques to the kernel packet forwarding? So this picture shows the architecture of the first prototype. And we used a FreeBSD 12 for base operating system. And they replaced the packet I/O part and IP lookup part, that's your one. And so I will explain the detail in the following slides. The first are applying fast packet I/O. So how to optimize the packet I/O part? So we applied M-switch, which is also called as value switch for replacing device I/O layer. So M-switch is our software running in the kernel and implemented by using NetMap framework. So what is NetMap? So NetMap is a fast packet I/O framework, which is a part of FreeBSD, and is also available as our external kernel module for Linux and Windows. And by default, M-switch has a L2 learning bridge function, and for the packets from the one virtual port to another virtual port. Note that when we use the M-switch by default, the packet do not go through the OS network stack. It is directly passed to the user application. But our goal is speeding up the general purpose operating system with L3 function. So we integrate the fast packet I/O framework and M-switch to the kernel network stack. So M-switch is used for the I/O part, and the OS stack is used for the process the protocol stack. So in this implementation, our M-switch receives the packet at the NIC, and then creates the fake and buff. The fake means the M-switch pre-allocated the network buffer in the switch fabric, and then pass it to the OS network stack. So the OS network stack stores the loading lookup results in the MBUF field, and then return the buffer to the M-switch. And then M-switch sees the lookup results, and then finally sends the packet to the destination port. Okay, so regarding the lookup part, we replaced our default large lookup with DXR. DXR is one of the existing research output. It is the fast IPv4 large lookup algorithm, which creates very small, compact data structure to fit into CPU caches. So how to use it? This time, we ported existing DXR patch for FreeBSD 12, and this DX function is called instead of our default large lookup function. This is the experimental setup for performance measurement. In this evaluation, the only single core is used for processing the packets. And there's two machines connected back to back. One is a Roto machine, which is installed our software, and the other machine is to use for generate the traffic, and just simply sending a packet from one NIC, and the router forwarding the packets from one NIC to another NIC, and finally this traffic machine receives the packets from another NIC. And the important thing is that so in this measurement, the packet size is 60 bytes. It's the shortest packet. It's excluding Ethernet RCLC. And traffic has the same destinations. And the routing table size is minimized. It means that now we are measuring the best case of the packet forwarding. So the maximum cache efficiency is available. And this is the measurement result. Our default throughput is 1.43 million packets per second. And replacing our I/O and lookup, or each of them affects the throughput, but this result also shows that even if we apply both fast packet I/O and load lookup, our function, it is still far away from our 10 Gbps line rate. It's 2.43 million packets per second. In addition, our M switch itself has the potential to forward the packet with 12 million packets per second. So we need to find where does the performance gap come from. So let's move to another measurement. Then we tried another measurement to know latency in detail. The goal of this evaluation is to reveal the time consumed by each function in the kernel. The methodology of this measurement is a bit tricky. The hard code, the output interface are in M switch. It means that when M switch receives any packets, it outputs the packet to the same interface, which is connected to the receiving machine. And so we put the returning point to terminate our OS packet processing in several points to find the latency at each point. The result shows that the 62% of total time is used by L2 input and output routine in this case. This is the L2 input and L3 input, L3 output, and L2 output. And the important thing is that even if the size of routing table is minimized, our L2 input and output consumes over 250 nanoseconds to process one packet. So please remind that the time budget per packet is to achieve maximum packet is only 67 nanoseconds. So it consumes a lot of time in the L2 layer. So this is the takeaway from these results. So the packet I/O is fast enough today, but the L2 input and output code parts are very expensive. So to achieve further speed up, we need to bypass these expensive functions. So this is second design implementation. So from the takeaway, we designed our new function to achieve the further speeding up. The basic idea is the conditionally bypass expensive code paths at both input and output. So in this picture, our Ethernet layer, this layer is our processing is target to reduce the overhead. So this time, we're just focusing on our speed up the L3 function. So for input bypass, we add the filter function at the M switch layer. The M switch looks a packet, and if it matches some conditions, this time L3 lookup, it's the IPv4 and they need to look up, and then the packet is directly passed to the IP layer in the bypass IF input or in the Ethernet layer routine. And this is our input path modification. For output bypass, we extended our DXR's table to store Ethernet header information corresponding to our next hop IP address. So once the MAC address is cached, our subsequent packets can use their Ethernet or header cache information and can bypass the Ethernet layer routine, including our up lookup. And the caches are varied within the batch, because M switch is batching the packet in the switch fabric layer. And so within within the batch, this cache is available. So this is the final the result of our performance measurement. And this graph describes the throughput of 5 different modules. And x-axis is the size of the packet. And to know which improvement affects the performance, we created and ran 4 versions of our router software. So all our implementations are equipped M-switch for packet I/O and DXR for router grab. And therefore, the difference among these 4 modules are the difference of the difference level of the bypass. The non-bypass blue one label shows the performance without bypass components. Our input bypass version only implements our quick protocol filtering functions for input. And output bypass has only the feature of output bypass. Input plus output means that the version employs both features. The most right bar, the gray one, shows the maximum packet rate at the rate of each packet size. So, for example, the shortest packet, the 14 million packets per second, is the maximum packet rate. And the native FreeBSD and our new module without bypass function because our line rate at almost here, 500 packet size. But our full implementation, it means our input plus output bypass, reaches line rate shorter packets are 252. And at the minimum size packet, our software increased this rate to about over 5 million packets per second. So which is a factor of a 3.8 improvement of forwarding speed. The other graph reports the relation between throughput and the batch size in M-switch layer. So the batch size varied from 1 to 1024 with 2 different packet sizes. The original M-switch papers shows that the throughput of M-switch itself is highly depending on the batch size. So we expect that our implementation is also affected by the batch size because both of the alternation of M-switch performance and the duration of cache effect. The throughput increases with the growing of the batching size and reaches its peak at 256 or 512 packet then and does not change after that. So when the batch size is small, not only cache expiration time becomes short, but the performance of M-switch itself becomes worse because of packet processing overheads. This curve is very similar to the figure that it's the figure on the M-switch paper. So this is why the throughput with the small size batch are slower than just without output bypass effects. From this variation result, it can be said that the changing of M-switch performance has strong affection to the throughput compared to the cache efficiency. Okay, let's go to the discussion. So from this result, our new logic can reduce over 80% of the cost, both our input and output. And also we can see that the accelerate the default FreeBSD IP forwarding rate, it's the 1.4 million packets per second by a factor of 3.8, and now reach to the over 5 million packets per second with minimum sized packets. And then the other measurement shows that the cache creation cost appears relatively cheap, comparing with the batch size of effect to the M-switch fabric itself. And now, as a conclusion, so we addressed the problem about user space networking. It is a very good solution to improve the performance of our IP forwarding, but there are many problems in production system. So our approach is the fast kernel-based packet forwarding. And here we applied 3 optimization. So the first is the replace packet IO part with M-switch, and also replace root lookup with the new algorithms. And then to achieve the further speed up, we implemented the bypass functions to bypass expensive routine at both layer 2 input and output. And then finally, we reached the result that are 3.8 times speed up to the default FreeBSD. And we could demonstrate the possibility of our kernel-based packet forwarding. Okay. So actually, there's a lot of work left, and some has already done, and the other are just in progress. I hope I can continue in semester break something. So this is the end of my session. So thank you for listening. Do you have any questions or comments?
What was the main reason to only use a single core? What was the main reason to only use a single core?
The reason is just want to see the pure performance in the single core. If you use the multiple core, it's of course we can increase the performance, but in the reality, we use the server. It's not only for IP lookup, so the application uses the cores in many ways. So the first I need to speed up with the single core, and of course I need to do more measurement with multi-core scalability. Yeah, but the first I just focusing on the single core. Yeah.
So you are getting the speed up of 3.8 times.
Yeah.
For have you also done testing on iMix, on mixed packet sizes?
Mixed packet sizes?
Yes, I mean you are only looking at small packets.
Yeah, small packets. Yeah.
So if you mix packet sizes, does that scale as well?
Yes. Yeah, because the shortest packet size could be the worst case because it's more difficult to saturate the bandwidth. So if we use the larger packet, it's very easy to reach the line rate.
Yeah. In a normal situation, you would get a mix of.
Yes. Yeah.
So for a normal workload, how much of a performance gain do you get?
I didn't that kind of measurement now, but yeah, you're right. So the real workload is different. There's a lot, the different packet size and different destination. Yeah.
Well, one of the problems with normal workload is it depends very much on the environment, what is normal. And usually what you see is that half the packets are like 60 and the other ones are like the huge one in a server, for example, an FTP server. And one direction they are very small and the other one is pushing payload. But for email services, it might be different, depends very much on the application. I have one question.
Hi.
The layer 2, the default layer 2 functions in FreeBSD. Do you have any idea why they are so slow?
Yeah, because the layer 2 are the main function in the layer 2 is our dispatching the packet to a lot of protocol stack, because there's many variety of our layer 2 protocol, so they just look up which protocol, and so yeah, that dispatching part is very heavy to process the packet.
No further?